The sun is the source of all life on Earth. Plants photosynthesize and produce fruits and grains with sunlight. Even plankton in the ocean feeds on solar energy, which forms the basis of the marine ecosystem. Without the sun, there would be no Earth's ecosystem. Furthermore, most of the organisms on Earth have their biological rhythms synchronized with the sun. We wake up in the morning and sleep when the sun sets. If the sun were to disappear, Earth would lose its life. The sun can be considered the source of everything that happens on Earth and the mother of all life. But how did the mother of all life, the sun, come into existence? Did it just magically appear one day? Well, let's find out how the sun was born. The gas and dust floating in the universe are called interstellar matter. This interstellar matter exists between stars or around stars. Generally, interstellar matter is composed of 99% gas particles and 1% dust. This gas is mainly composed of about 90% hydrogen, 10% helium, and a small amount of heavier elements. When this interstellar matter contracts due to gravity, it forms giant clouds called nebulae. Stars are born from these interstellar matters. When the density of a nebula increases as it collects more and more interstellar matter, the nebula starts to collapse due to its own gravity. The nebula contracts into a sphere, and its center becomes denser. The density continues to increase, and gravity also becomes stronger, so the contraction continues. Due to the high density, atoms collide with each other. The gravitational energy is converted to heat, and the central temperature of the nebula increases. Now the nebula seeks a balance between two forces: gravity that tries to contract toward the center and energy that tries to push it outwards due to gas rotation, etc., toward the outside. These two forces find equilibrium and reach a stable state. The gravitational contraction stops, and the nebula does not expand. Now, a protostar is born. Primitive stars that emit light by themselves with high density and temperature are born now, but they do not stop growing. The center of the primitive star contracts and expands repeatedly, constantly devouring the surrounding interstellar matter and growing. The mass of the primitive star gradually increases, and the temperature and density increase as well. The hot temperature at the center of the primitive star is transmitted to the outside through convection, and the primitive star begins to gradually brighten. This process continues. However, at some point, something amazing happens. When the internal temperature of the primitive star reaches 10 million degrees, nuclear fusion reactions begin at the core. A star that emits light on its own, like the sun, is born. A star that burns hydrogen through nuclear fusion reactions like the sun is called a main sequence star. Let's take a closer look at the nuclear fusion process of this main sequence star. First of all, nuclear fusion is a reaction in which atomic nuclei fuse together to form a heavier nucleus. For nuclear fusion to occur, the temperature and pressure must be sufficient. If the energy is low due to low temperature and pressure, the electrostatic repulsion between atomic nuclei prevents them from sticking together. This is similar to the phenomenon of trying to force two magnets with the same polarity to stick together. In general, atomic nuclei cannot combine under normal conditions of temperature, density, and pressure. In a primitive star with low temperature, density, and pressure, even if hydrogen is accumulated in the center, nuclear fusion does not occur. On the other hand, if extremely high temperature and pressure conditions, like the nucleus of the Sun, are formed, the distance between atomic nuclei is reduced, and neutrons exert a force called nuclear force, which connects nuclei to nuclei. This way, atomic nuclei come together. In the center of a star, 4 hydrogen atoms fuse to form helium. In this process, about 0.7% of the mass disappears, and according to the mass-energy equivalence principle, about 0.7% of the mass is released to the outside in the form of energy such as light and heat. Photons are born in the center of the star through nuclear fusion reactions. The time it takes for photons to reach the surface of the Sun is a whopping 1 million years. The sunlight we see has taken 1 million years to travel from the center of the Sun to escape. When we look up at the night sky, we see starlight. This starlight comes from stars that are undergoing nuclear fusion somewhere in the universe. The Sun burns around 400 to 600 million tons of hydrogen per second. The resulting helium is accumulated at the center of the Sun, and when a primitive star begins its fusion reaction, the gravitational contraction stops. Nuclear fusion occurs in the high-pressure environment at the center of the star, and energy is emitted. This energy is then tightly squeezed by the immense gravity of the star. The force of pressure and gravity balances each other, and the entire star becomes stable. It continues to undergo nuclear fusion without increasing or decreasing in size. Our Sun has maintained this state of energy equilibrium for roughly 5 billion years. Although 5 billion years is an eternity by human standards, for stars, This is just the beginning of middle age. The main sequence phase occupies the longest period of a star's life. Looking at our baby sun, which has now become a main sequence star, it currently has about 80% of its luminosity. However, over the course of 5 billion years, it has gradually become brighter and has acquired its current brightness. The Sun will remain a main sequence star for another 6.3 billion years. The Sun will continue to get hotter and brighter. In approximately 700 million to 1 billion year, the energy emitted by the Sun will become too high, and the temperature on Earth will rise, causing most of the planet's living organisms to disappear. Nuclear fusion reactions will continue to occur at the core of the Sun, but the hydrogen that the Sun can burn will decrease over time, and the resulting helium will increase. As the helium increases, the average molecular weight increases, and the core of the Sun contracts little by little due to pressure, causing the density and temperature to rise. As the internal temperature of the star rises, the surface energy becomes larger and the star becomes brighter. In the case of the Sun, it will remain a main sequence star for a relatively long time. However, the period during which nuclear fusion occurs is determined by the star's birth. Stars with lower mass relatively hold onto their energy for a long time in the main sequence phase, since they release energy weakly. On the other hand, stars with greater mass emit tremendous energy in a short amount of time, causing them to quickly deplete their energy and move on to the next phase. Stars either live thin and long, or thick and short. It is fortunate if they only make it to the main sequence phase. Not all nebulas or protostars in the universe reach the phase of the second sequence. Objects with a total mass of only 1/10 of the solar mass, much smaller than the Sun, cannot generate enough temperature or density to undergo hydrogen fusion and instead, slowly burn deuterium or lithium before becoming brown dwarfs that die out. If Jupiter had a much higher mass, it may have undergone fusion. Our solar system almost became a binary star system. But becoming a celestial body is not an easy feat. However, there is something we are curious about. What will happen to the Sun once it burns all the hydrogen in its core and only helium remains? Will the Sun stop, like a car running out of fuel? In the next lesson, we will learn about the next evolution process of the Sun, becoming a red giant.